Ok, bonjour à tous. Nous allons commencer cette session. Je suis Boris Pioline. Et au nom des organisateurs, c'est un grand plaisir de vous accueillir à cette session grand public de la conférence StringMat 2016, qui est aussi la 21e session du séminaire Henri Poincaré, Bourbafie pour les intimes. Avant toute chose, je voudrais annoncer un changement de programme que vous voyez ici sur l'écran. Donc malheureusement, le professeur Nigel Hitchin n'a pas pu venir. Et donc, l'exposé de l'après-midi de professeur Akani Hamed est avancé à 15h30, donc après une pause café qui le séparera de l'exposé précédent. Donc, je vais passer en anglais, car comme vous pouvez le voir, les exposés aujourd'hui seront en anglais. So, welcome everyone to this general public session of the StringMat 2016 conference, which is organized jointly with the seminar Henri Poincaré and in partnership with the Clay Mathematics Institute. As you've just heard, there is a small change of program, which you can see on the screen. So the StringMat conference has been taking place here at Collège de France since Monday. It has gathered over 200 physicists and mathematicians from all over the world to discuss exciting new developments at the juncture between theoretical high-energy physics and mathematics. So for those foreign to this field, it may come as a surprise that mathematicians and physicists have anything in common besides the use of Greek alphabet and calculus. But in fact, as will hopefully become clear during these 4 lectures today, over the last 30 years, there's been a very intense dialogue between the two communities, or at least between those sub-communities interested in such topics as topology, algebraic geometry, number theory on the math side, and particle physics at the highest available energy scales on the physics side. So the stage on which these two communities have come to face is face-to-face, is quantum field theory, and more specifically string theory, which is a general framework proposed in the late 60s, early 70s to unify all fundamental forces in nature under the roof of special relativity and quantum mechanics. So this 40-year-long quest to achieve this goal, and indeed to understand what is really string theory, has uncovered profound connections with many fields of mathematics, has opened new avenues for particle physics, for theoretical physics more generally, and it has opened up new branches of mathematics. And this is the topic of this session today. Physics intuition has provided completely new points of view on objects that mathematicians thought they completely understood. And it has motivated many deep conjectures, which they, mathematicians, have been able to prove using their own rigorous methods. So I will not say more about it, because we will hear abundantly about it today through this session. And instead, I will introduce our first speaker today, Professor Hiroshi Oguri from California Institute of Technology in the US, Caltech, and also from the Kavli Institute for the Mathematics of the Universe in Japan, APMU. And he's going to introduce us to the theoretical challenges posed by the weakest of all fundamental forces in nature, which is also the most relevant one at long distances, namely gravity. So after 2 years in the graduate school at Kyoto University, Professor Oguri became a tenured faculty member at the University of Tokyo before getting his PhD from the same in 1989. In 1994, he was appointed professor at Berkeley, and he stayed there until 2000, and he became, at that time, a professor at Caltech. So currently, Professor Oguri is the Fred Kavli Professor of Theoretical Physics and Mathematics and the director of the Walter Burke Institute for Theoretical Physics in Caltech, a newly created institute. He's also the principal investigator of the Kavli Institute for the IPMU in Tokyo. Professor Oguri has received numerous awards and honors, including the Heisenberg Prize for Mathematics and Physics, the Humboldt Research Award, the Nishina Memorial Prize. He's a member of American Academy of Arts and Sciences, Simons Investigator, and the trustee of Aspen Center for Physics. But besides his outstanding involvement and engagement in research, Professor Oguri is also very active in science outreach. His 4 popular science books have been sold over 250,000 copies in Japan. His book in Superstring Theory was selected for the 2014 Kodansha Prize for Science Books. He's a contributing writer for Asahi Shimbun, a leading national newspaper in Japan. And well, most recently, he served as a science advisor to the 3D dome theater movie called The Man from Nine Dimensions, which debuted in Tokyo this April, and I learned has just received the 2016 Best Educational Production Award from the International Planetarium Society. So we very much hope that we have the pleasure of seeing this movie in Paris soon. It was not possible to organize it today, unfortunately. So, Professor Gray, many thanks for accepting our invitation to speak at this joint public session. And please tell us, what is gravity?
Okay. Okay. Thank you, Boris, for your very kind introduction. And thank you all for coming on this beautiful Saturday morning in Paris to hear about gravity, monodromy, quantum geometry, and the end of space-time. So I would like to tell you about what we know about gravity. So let me turn it on, and I'm supposed to have 1 hour, I believe. So it started. In fact, this is a very nice venue, and for those of you who are not involved in this strings mass conference, which this is the last day of the conference, and in fact, this talk is for those of you who are not at this conference. We had this very nice conference, about which I will tell you more about later in the talk. But this is also a very nice place for me because 12 years ago, our friend in Paris also organized the annual Strings Conference 2004 at this exactly the same venue, and we see that we took group photo around the same place. And in fact, I was asked to give a summary talk at this conference, and I remember sitting on that corner, listening every talk, taking notes to give a summary talk. And you see, actually, I'm here. And I'm here with actually my daughter, who was 4 years old at that time. She's 16 now, so I don't think I can do that anymore. So it's kind of a nostalgic occasion. So today I'd like to tell you about gravity. And of course, we all think that we know about gravity. Gravity is the most familiar force in nature. But it's actually, I would like to tell you that it's the most mysterious of all the forces. And it actually also holds the key to some of the deepest secrets of the universe. So this is actually the first of 4 public lectures scheduled for today. So I'm sort of appetizer for the rest of the 3 talks. So my talk will be intended to be very sort of general public and want to motivate you to learn more about this in the following 3 talks. So I thought I should organize my talk according to 7 wonders of the world of gravity. You might have heard, of course, about the 7 wonders of ancient world. I was told that there was a time of the history when all of these 7 objects, including a pyramid in Giza and Hanging Garden of Babylonia, existed. And so it was sort of a tour guide or Michelin in the ancient Mediterranean world. And so today, I'd like to give you a tour of the world of gravity. So I organized my talk according to 7 questions or mystery of the gravity. And the first mystery is actually the gravity is a force. And of course, these days, we take it for granted. But it wasn't obvious for people in the ancient world. For example, Aristotle thought that the gravity is actually not a force, but it's just a reflection of the tendency for object to try to go to the center of the Earth. That all the objects are made of 4 basic constituents, and we are mostly made of earthy object, which wants to go back to the center of Earth, just like a bird which lays the nest in the morning want to come back to the nest in the evening. And it wasn't such an absurd idea because these days, of course, we know that there are planets and other stars that attract and interact with each other by gravitational force. But of course, originally, we only know the gravitational force in one direction, and it was more attractive to try to understand it as a tendency of the object try to go to the center of the Earth. And this kind of view lasted for 2,000 years. And the change of the view, in order to change this kind of view, it's actually very important to define the object or concept properly. So we have been doing this, we have been having this conference of the interaction of physicists and mathematicians. And what mathematicians always tell us, physicists, is that it's very important to define things and to understand their concept exactly. So similarly, in the case of force, we need to actually define what the force is. And that's one of the things Newton did. What are the forces? And so Newton defined the force as something that changed the motion. If there are no Earth here, this ball, which is something that is happening this week in Paris, I understand, would just go straight. But because of the gravitational attraction, it changed the shape of the trajectory. So that, according to his definition, is the existence of the force. So now we understand that there are actually 4 forces in nature: gravitational force, electromagnetic force. Those are understood 400 years ago. And in fact, the understanding of electromagnetic force were earlier. But then in the 20th century, we came to realize that there are actually 2 more forces in nature: strong force and weak force. Strong force attracts quarks, which are constituent of elementary particles, such as protons and neutrons are made of 3 quarks. And pions, which mediate force between these elementary particles, consist of 2 quarks. And strong force attracts quarks to each other and make those particles. Weak force is responsible for radioactivity, sunshine, etc. And of course, we are in Paris, where the radioactivity was discovered by Becquerel and developed further by Marie Curie and many other chemists and physicists who are working in Paris. And so one of the realizations of the weak force that came with the realization of the existence of weak force and strong force is that we have to enlarge the concept of force. So at the time of Newton, the force was understood as something which changed the trajectory of particle. But in the case of weak force, it's also changed the type of particle. So you have to enlarge the concept of force as something which changes the condition or the state of the object. So trajectory or velocity is one type of state, but type of particle is another. And changing that should also be understood as force. At any rate, we now understand that there are actually 4 types of force in nature: strong, electromagnetic, weak, and gravity. And among them, it turns out that gravity is the weakest of all the fundamental forces that we know. So that's the second wonder of the gravity. The gravity is the weakest of all forces. So you might think that that's absurd, that this is the strongest force that we feel every day. That's why you are sitting on the chair of this auditorium and not floating in the air. But if you think about it, it's actually opposite. For example, usually I bring this prop with a small magnet. But if you think about the magnet here, and then suppose you have some kind of metal clip or something, then if you approach the magnet to the clip, clip is going to jump to the magnet. So that means that actually the magnetic force from the magnet is stronger than the gravitational force from the Earth. And the magnet is just a few grams, whereas the Earth is billion times billion times billion grams. So that means that the magnetic force, even though it's exerted from very tiny object, is much stronger than this big the gravitational force from the Earth. There is another way to think about it. So for example, I'm standing on this podium, and it's not going under the Earth. If I bang on this table, it's actually quite, I did it too much, so it's anyway, so it's hard. But it's hard because it's very solid. And it's very solid, but partly, well, one of the reasons to understand it is it's an electromagnetic force. That there are lots of electrons in my hand, and there are lots of electrons on the table, inside of the table. So if I bang it, there is a electromagnetic repulsion between them. And that's why I cannot put my hands through the table. And that's why even though I'm feeling gravitational attraction, I won't go under the podium. So this is another demonstration that the electromagnetic force is actually stronger, much stronger than the gravitational force. And so gravity is not only weakest of the four forces, all the forces, but it's actually much, much weaker. And in fact, that's one of the mysteries of the gravitational force that we actually do not quite understand. So I'm going to actually tell you various mysteries of the gravity today, some of which we understand and some of which we are actually still developing. And this is one of them, why gravity is so weak compared to other forces that we know. The third mystery is actually you can turn off gravity. So even though you feel gravity every day, but you can arrange so that you can turn off gravity. So here is an example. So of course you know this gentleman, Stephen Hawking, one of the very important contributors to the study of gravitational force and other aspects of fundamental laws of nature. And he's floating. The gravity is turned off inside of this room. Of course, what is happening is that this is a free fall. So you have an airplane, and all the windows are sort of closed so that you can see outside. And then the plane, if I do this, drop this, then I'm going to damage the podium. So the plane just goes free fall. And of course, eventually it's going to turn on the engine and then go up again. But for this brief period, you feel that the gravitational force is turned off. And of course, this is something you also feel. For example, when you are riding on an elevator, when the elevator goes up, you feel that your gravitational you weight a little bit more. You feel you weight a little bit more. So that means that gravitational force is getting stronger. When the elevator goes down, you feel that the gravitational force gets weaker. So this is a sort of exaggerated situation where in the complete free fall, the gravitational force is turned off. So it seems as though that the way gravitational force acts, depending on your point of view, and this is actually this is an observation that Einstein called the happiest thought of his life. So as we will see later, Albert Einstein in 1905 made three important discoveries, one of which is the discovery of special relativity that we'll talk about later. Another is the explanation of Brownian motion. And third is the explanation of photoelectric effect, which is sort of precursor to quantum mechanics. But even though he made these three important discoveries, but he didn't immediately get an academic job. So for the next 3 years or so, he was still working on the patent in the patent office. But his boss realized that Einstein is actually really talented, so he actually gave him a lot of free time to think about things. So he was sitting in his patent office, and then one day realized that for an observer falling freely from the roof of a house, the gravitational force does not exist. And this led to his construction of general theory of relativity 10 years later. So, but that requires some more study, and that's why it took him 10 years to come to general relativity. And that is that he actually started from this observation and realized that you can actually describe gravity as warping of space and time. So it took him 10 years to turn this idea into mathematical reality. So in order to discuss that, we need to understand what is space and what is time. And this is, again, one of the things that people have been pondering and thinking about for thousands of years. And it, again, go back to Aristotle. He made a famous statement that nature abhors a vacuum. And sometimes this statement is referred to as saying that, well, it's very hard to make a vacuum because you have to extract the air. But it's not as simple as that. He thought that space and time are defined in such a way that it describes the matter in it. So, for example, the space is there to tell you where the object is, and the time is there to describe how it developed. So without matter, there is no space and time. So that was his idea, that was the reason for his statement that nature abhors a vacuum. So in his point of view, the space and time are closely tied to the matter and object in it. this type of idea was sort of totally changed by Isaac Newton. So he introduced a concept of absolute time and absolute space. So absolute time is something that flows uniformly from infinite past to infinite future. And absolute space is there, independent of what's happening inside of it. So for him, space and time is something like a theater or stage where things happen. So this is a kind of idea of space and time that we are familiar with in everyday life. So for example, when we go out to work in Paris, we often consult our appli on my iPhone or smartphone to tell us exactly where we are. And so these days, the watches and iPhones and the smartphones are so accurate that everybody have exactly the same time. And so Boris will tell you when I should stop my talk. But so this kind of idea of absolute space and absolute time is a very familiar concept. But this was invented only 400 years ago. But since because of this Newton's idea of classical mechanics has been so much used in our everyday life, so we take it for granted. But in fact, 100 years ago, by Albert Einstein, this concept was again totally revolutionized. And not only the space and time depends on observer, but it also depends on how things is happening inside of it. So the first half of the revolution is a concept that space and time depend on how you observe it. So let me demonstrate how he came to this idea. So suppose you have two people in a room, and then suppose they are captains of baseball team, and they want to decide who goes first and who goes next. And I don't know, in France, do you know the concept of stone, scissors, and paper? Do you do that as a kid? So they decided that they figured out that they can actually fairly decide who do that by doing this. That's a stone, paper, and scissors. And so there is a light source in the middle, exactly in the middle. And then judge turns on the light signal. The light propagates at the same speed. And then when they see it, they do this. So for example, this captain has stone, then this captain has paper. So he won. But it turns out that there are people who are actually observing it from outside of the room, and they claim that they are not fair. This wasn't fair. Because it turned out that they are riding a train, and the train was going very fast, very close to the speed of light, very unrealistic, but suppose that was the case. Then in that case, actually, as the train was going in this direction, if the speed of light is the same independently of how fast you're going, then the light comes to him before the light reaches the other person. So this doesn't look fair because indeed, actually, he won. So this looks very suspicious. So this demonstrates that concept of simultaneity, depends on how you observe it. From those two people who are inside of this train, it looks as though they are doing this simultaneously. But for those people who are watching it from outside, these two events are not simultaneous. So Einstein realized that if you accept the point of view that the speed of light is independent of how you observe it, then the concept of simultaneousness has to be modified. He even went further and said that actually if you have taken into account the gravitational force, then the matter in it and energy in it also modify space and time. So this is sort of a caricature. Now, it's kind of difficult. So this is supposed to be for general public. I saw there are some mathematicians, but I totally ignore them. And so I will try to explain how actually the modification of the space and time changes, give rise to effects that mimic gravitational force. So it's kind of hard to explain that in our three-dimensional space. So let's just postulate that we live in two spatial dimensions. So there is actually a very nice novel written in 19th century Victorian England called Flatland. So this is a story about people who are living in two-dimensional flat space. And So it's a Victorian world. It was very hierarchical. So there are various different types of people. There are triangular people, which have 3 edges. And there are square people, and pentagon, octagon, etc. And as the number of edges increase, you are more higher in your social hierarchy. And clearly, circle is at the highest of the social hierarchy. So this story is about Mr. Square. So Mr. Square was one day, so he's like a middle-class man, walking in the street of flatland, and then noticed something in front of him. And then there was like point, dot. But then it came out, became circular. So this is clearly somebody who is superior to him. But then it became larger and larger, and they shrunk and disappeared. So he wondered what happened. So what happened was that it turns out that even though those people are living on this flatland, but they were actually embedded in 3-dimensional space. And then there was ball living in it. And the ball was actually visiting the flatland. So eventually, Mr. Square became friendly with Mr. Ball, and Mr. Ball took him to the 3-dimensional world, and then Mr. Square realized what is the kind of space that he was living in. And then he went back to flatland and tried to explain that to everybody, and nobody believed him. So this kind of story. So anyway, so suppose Einstein was in this flatland. What kind of gravitational theory that he would have invented? If I actually reduce the 3-dimensional, the Einstein theory in 3-dimensional space to this flatland, then his theory would look like this. So let's get a piece of paper, and suppose you put some heavy object in the middle. What this object does to this 2-dimensional world is that it creates what's called the deficit angle, which is the following concept. So if you have a point, and then if you go around the point, as elementary school or junior high school geometry tells you that you are going around 2 pi, namely 360 degrees as you go around. However, if you have heavy object here, according to Einstein's theory in 2 spatial dimensions or flatland, then you eat part of this angle, and then it becomes like a cone. So now, as you go around here, so you ignore this point anymore, then it's less than 360. And so this is the deficit angle. It's deficit from 360. And the heavier the object, the bigger the deficit angle. So what happens is that if you have, say, for example, deficit angle here, and if you have 2 straight lines, so this object in flatland just try to go to straight line. However, since there is a deficit angle, so they actually converges. They look like they converge if these are glued together. So because of the deficit angle, these 2 blue particles travel just as if they are attracted to this heavy object here. So therefore, according to this rule, if you have a heavy object, the shape of this 2-dimensional surface changes, and that acts just as if there is a gravitational force acting on it. So Einstein's idea is essentially the same in 3 spatial dimensions also, although it requires a little bit more mathematics. But it's also important that gravity also warps the time. Namely, it changes the way that the time flows. And in fact, in our everyday life, for example, the kind of gravity that we feel on the Earth, this effect is more important. So the gravitational force changes the motion of particle and other objects by modifying the geometry of the space, but also changing the way that time flows. So for example, when Einstein calculates the bending of light near the sun, he discovered that the amount was twice as much as that you'd have obtained if you just used Newton's theory. And the factor 2 came from the fact that the gravity from the sun modified the geometry of 3 spatial dimensions near the sun, but also changed the way that time travels, time flows near the sun. And these 2 effects combine to give you factor 2 in that case. The most extreme situation to demonstrate the warping of time happens near the black hole. this is an extreme example of warping of time. The black hole is an object that is so heavy that even the light cannot escape from it. So namely, the escape velocity from the surface of black hole is the speed of light. And so therefore, nothing can come out from the black hole. But even nothing can come out from the black hole, when you go inside of the black hole by free fall, if the size of the black hole is large enough, then you shouldn't, according to Einstein's theory, feel any force except for tidal force when the size of the black hole is small, because of this equivalence principle that we talked about. Namely that when you are freely falling, you don't feel the gravitational force. So therefore, I get a mission from my wife to explore the black hole. So she tells me, so this is supposed to be black hole. And near the black hole, there is a surface of no return where the escape velocity is the speed of light. And then I was instructed to explore this area. So I promised her that I'm going to send her email every day to report what's happening. So for the first few days, she gets email from me every day. But eventually, it became once a week, once a month, once a year. And then she stopped receiving email from me. So, but that's not quite fair, because I think I'm sending her email every day. But she doesn't think so. So she thinks that I'm actually procrastinating near the black hole, trying not to get inside of the black hole, even though I'm sending email to her every day and, in fact, going inside of the horizon. So this is an extreme case where, depending on observer, how the time flows how the time looks to flow differently. So from her perspective, the time near the black hole is flowing very slowly. So I'm not going inside of the black hole anymore. But from my perspective, since I'm freely falling, so I'm not feeling gravitational force, so I can just go straight inside of the black hole. So this is another way that gravitational force changes the way that the time flows. This is a very foreign concept, but this is actually used in our everyday life. In your iPhone or smartphone, we have this map app which tells you where you are. And this makes use of a global positioning system that most of which was launched by United States. And there are like 20 of them going around the Earth. So each of them has a very accurate clock, the atomic clock, which sends signal at a very accurate rate. And what happens is that if you look at the sky, and if you see at least 4 of them, and get the time from each one of them, then you can just simply solve the linear equation to find out where you are and what time it is. You need to see 4 satellites because you need to know your 3 spatial coordinates and 1 time. But in order, of course, for you to be able to understand where you are and what time it is, the clock has to be accurate. But since these satellites are flying at a very high altitude, so that means that gravitational force is weaker. Gravitational force is weaker, so that means that time is actually clicking faster. At the same time, these satellites are moving very fast, so that means that there is a special relativity effect of clock is actually seen as if they are clicking slower. So combining these effects, and please excuse the unit of length that I'm using here. This slide was prepared for American audience. And, but if you take into account these effects, then you would get an error of 7.5 miles per day. So that would be totally useless. So if Einstein were not born in our world, then we would have encountered a very funny situation. Because most of the technologies that we employ to develop GPS and launch them would not require neither special or general relativity. So you could imagine a planet where you have advanced civilization, and they launched GPS without Einstein, and they realized that it was totally off. So they had to figure out what was the cause of such an error. So fortunately, we had an Einstein. So we knew in advance that we had to calibrate these effects. Okay, so anyway, so 1915, which is 101 years ago, Einstein presented his equation of gravitational force at the Prussian Academy of Science in Berlin. And next year, the following year, 1916, he predicted gravitational wave. His first paper was not quite right, so he revised it into 2 years later. And 99 years later, September 14, last year, LIGO Observatory, Laser Interferometer Gravitational Observatory, made the first direct detection of gravitational force. So this is one of the LIGO observatory with 4-kilometer arm. They have laser light going back and forth, measuring the length of this arm, or in fact, the relative length of these two arms. So when the gravitational waves come through, then the relative length changes, and that is what is being measured. And this was reported, for example, by New York Times above the fold, in the front page. So amazing thing is that so you have actually two of these observatories, one in Hanford, Washington, and the other in Louisiana. And these two waveforms totally coincided, just like here. So this gravitational force was emitted by a pair of black holes about 30 solar mass each. So it's a big black hole. And in fact, I was told that for astrophysicists, these are surprise because they had never observed such heavy black hole. And they actually do not have good idea yet of how such big black hole should have formed, 1.3 billion years away. And these two observatories detected identical signal. And also, they were prepared for it, so they actually calculated exactly what kind of waveform that you'd observe by using numerical general relativity, the computer simulation of general relativity. And that also agreed. So that gave us confidence that they actually observed the merger of two black holes. So Caltech is actually one of the two major contributors to the project. The other is MIT, and we have a headquarters of LIGO laboratory at Caltech. So when this was announced, we had a gathering at Caltech. The announcement itself was made at the National Press Club at Washington, D.C. So I took this photograph, and I got some souvenir. But anyway, the important thing is that this detection of gravitational wave confirmed Einstein's prediction 99 years ago, in fact, 100 years ago from today, and opened a new window to the universe that until this time we were observing the universe using electromagnetic waves like light or X-ray. But now we have a totally new way to observe the universe, and it opened the possibility to test Einstein's theory at strong gravitational fields and see whether the theory should be modified or not. There is actually a very nice news last month where the second detection was announced. So the first one was not coincidence. And again, these were very heavy black holes. So these purple objects are black holes that had been observed before the gravitational wave detection by X-rays. And the one detected by gravitational force are heavier than those. So it looks like there are actually things that we don't yet understand at the universe that are being revealed by the gravitational waves. And now we have two samples, so we can sort of estimate how frequently that we're going to be observing the gravitational wave. And in fact, the LIGO laboratory is actually undergoing improvement. And I'm told that in a few years, the sensitivity would increase from 3 to 10. But if you increase sensitivity by 3, then actually the volume of the space where you can observe would be cubed. So it's going to be either 27 or 1,000 times more frequent than we are doing now. So it is estimated that the LIGO detector will start detecting like 1,000 gravitational wave events from black hole merger per year. So that's going to be very exciting opportunity. So anyway, so this is about half of my allocated time, and this is exactly half of my presentation. So I started out saying that gravity is a force, which for us it's obvious, but it wasn't obvious to ancient Greeks. And gravity is also weak, which is surprising, but it is true. And the important observation by Einstein is that it is in the eye of the beholder. And he formulated it as that the gravity is warping of space and time. So the title of my talk is what is gravity? And Einstein gave the answer that it's warping of space-time. So I could finish my talk now. However, I still have 30 minutes, so I should go on. And in fact, it would have been a good answer, except that quantum mechanics, except that we actually also discovered quantum mechanics. And that changed the whole thing. So in fact, gravity is very hard to marry with quantum mechanics. So 4 years ago, 4th of July, which is the day after tomorrow, the CERN laboratory in Geneva announced the discovery of Higgs particle. So this is Professor Peter Higgs. And this is the front page of New York Times with autograph by Peter Higgs. And so one of the important point of this discovery is that this completed the standard model of elementary particles. So standard model was sort of constructed by theoretical physicists decades ago, and essentially sort of completed in mid-70s. But there are 17 elementary particles in the standard model, but Higgs particle was not discovered until 4 years ago. So this is actually sort of stuffed animal toys of standard model elementary particles that you can order online. And this was actually, I copied it 5 years ago. So at that time, Higgs boson was not discovered, so this was sort of in the category of theoretical particle, and these were detected particle, but now it should belong to this category. So this is this complete the sort of current standard model of elementary particle essentially describe all high energy physics phenomena that have been detected in the laboratory, except for mass of neutrino, which require some slight modification to this table. However, this is not the end of the story, because in fact, if you go to this website, there are actually two theoretical particles listed in this category. One is Higgs boson, but the other is graviton, which exchanges the gravitational force. So in this table of elementary particles, you have photon, which exchanges the electromagnetic force, gluon, which exchanges the strong force, and W and Z boson, which exchanges weak force. So those are 3 of the 4 fundamental force. But the subject of this talk today is gravitational force. And the particle that's supposed to communicate gravitational force has not been discovered. And in fact, including that is a very difficult thing in the theory of elementary particle. Partly because, as I explained, the gravity is warping of space and time. But on the other hand, things are intrinsically uncertain in quantum mechanics. In the classical world formulated by, for example, Isaac Newton's classical mechanics, the future is totally predicted. So for example, I throw this toward Boris. Then if I do it very well, I'm going to hit him. And it's totally predictable. Whereas in the quantum world, it's not clear what exactly the trajectory of these objects are. But if you combine that with gravity, that means that space and time become uncertain. And quantum mechanics and the standard model of elementary particle, for that matter, are formulated assuming that the space and time exist, and then in it, the theory is formulated. And the fluctuating world of space and time, it's not clear how you can formulate such theory. So reconciling quantum and gravity has been the holy grail of modern physics. It looks like in the Hollywood, these are also very important concepts that are sort of employed in the recent movies. But combining them has been sort of one of the very important questions, unsolved questions in theoretical physics homework from the 20th century. And so far, the only consistent way we know how to do this is superstring theory. Superstring theory postulates that fundamental building block of matters are not point particles. So these are not elementary particles, but elementary strings. And the vibration and the configuration and the wave function of these strings describe the 17 elementary particles in standard model of particle physics, as it is expected. So that is what is expected. And in fact, one of the reasons we are so much fascinated by string theory is that string theory actually seems to contain all the ingredients needed to build this table of standard model of particle physics, including graviton. Moreover, string theory helped solve some of the deepest mystery of quantum gravity, such as the origin of Hawking radiance from black hole, and led to new concept of space and time, such as holography. I imagine some of the speakers today may touch on it, so I don't have time to go much deeper into it. So as Boris said, I have been working with a team of very talented visual creators in Tokyo for the last 3 years to make a three-dimensional movie on superstring theory, and I was sort of scientific supervisor for this. The title of the movie called The Man from 9 Dimensions. I don't have time to explain where the 9 come from. But so I was very happy to report to you that last week this movie was selected as 2016 Best Educational Product Award from International Planetary Society. The competition was held in Czech Republic, and the award ceremony was at the biannual conference of International Planetarium Society in Warsaw, Poland. And from 66 films submitted from 15 countries. So I would like to actually show you a trailer of this movie. But I need to sort of warn you, explain you actually what you are going to see. So the movie is for 30 minutes. I'm not going to show you 30 minutes. It's going to be like 2 minutes. And so I have to, in 30 minutes, we have to explain quantum mechanics, standard model of particle physics, including Higgs effect, flavor changing neutrinos, and how the and then we have to explain Einstein's theory of general relativity, the evolution of the universe, dark ages, inflation, Big Bang, and then try to explain why it is difficult to marry quantum mechanics and general relativity, and how string theory solved all this. And the movie explains that in 30 minutes. So it's not so easy. So in order to actually sort of guide the audience through these ideas, we came up with a metaphor. So the man from 9 dimensions is a metaphor of theory of everything. And there is actually a group of 3 scientists who are chasing after this mysterious man from the 9 dimension. So this is a metaphor of scientists trying to understand the fundamental laws of nature. And through that process, the man takes us to the microscopic world of elementary particles, and then going back to the history of the universe and take us to the Big Bang, etc. So I'm going to show you the trailer, but this actually trailer focus on entertainment aspect of the movie, not quite scientific aspect, but the actual movie contains lots of scientific content. So I hope there will be opportunity for you to see the whole thing.
What am I? Why is the universe the way it is? How did it come into existence? The scientists are looking for me.
So this is the guy.
TOE? Yes.
Do you recognize Calabi-Yau manifold?
Find him, and we'll have solved all the mysteries of the physical world. All possibilities exist simultaneously. Dimension.
Okay, so that was the trailer. We are very fortunate to have been able to sort of get the service of a very talented visual creator. And in fact, Takashi Shimizu is primarily a horror movie director. He makes lots of horror movies. And so he was a lot of fun to work with because he came up with lots of visual images that I would not have thought about. But anyway, so I highly recommend you to, if you go to Japan, it's actually currently shown at the science museum called Miraikan. So, anyway, so marrying general relativity and quantum mechanics also poses lots of interesting questions in mathematics. And so that is the reason for this strings mass conference that we have been enjoying this week, thanks to the hospitality and organization by our friend in Paris. And it's partly because general relativity describes gravity in terms of warping of space and time, namely in terms of geometry, whereas quantum mechanics describes the microscopic world of elementary particles in terms of algebra. So the study of quantum gravity and string theory, therefore, is opening a new line of research in mathematics which connect geometry and algebra in unexpected way. So this is one of the reasons why this area has been so fruitful for both mathematicians, because it poses interesting questions, and also for physicists, because techniques developed by mathematicians have been turned out to be very powerful. So this kind of development also gave us lots of new insight into string theory, which led us to understand the theory and maybe possibly applications of the theory to important question about the universe. And one of the important questions I want to pose is, why is the sky dark at night? And this is actually closely related to the mystery of gravity. So I included it as one of the 7 wonders of gravity. So why is the night sky dark? Well, you say, well, because the sun is on the other side of the Earth. That's one answer. But it's not as obvious as that. So there are a lot of stars in the universe. And so suppose you have stars around us, and then there are more stars twice as far away. If you go twice as far as us, then of course light from each star is 1/4, because the strength goes like 1 over decreases like a square of the distance. However, if we go twice the distance, then there are actually 4 times more stars. So that means that sum total of light coming from these stars is actually the same as sum total of light coming from these stars. So if you go to twice as many, you get the same amount of light. If you go to 3 times away, you get the same amount of times. So if the universe is infinite, then you get infinite amount of light. So why is it that the sky is dark at night? The sky should be infinitely bright. So this is called Olbers paradox. You can try to avoid this question by saying that, well, there are dust in the sky, in the universe, etc. But dust absorbs the light, but then store energy and re-emit the light. So it won't help you. So this actually, the correct answer to this question was interestingly pointed out by Edgar Allan Poe in one of his last beautiful writing called Eureka. So let me read what he wrote. So, were the succession of stars endless, then the background of the sky would present us a uniform luminosity like that displayed by the galaxy, since there could be absolutely no point in all that background at which would not exist a star. So this is exactly the formulation of the Olbers paradox 20 years before. So he proposed a solution. The only mode, therefore, in which under such a state of affairs, we could comprehend the void which our telescope finds in innumerable directions would be by supposing that the distance of the invisible background so immense that no ray from it has yet been able to reach us at all. So this turned out to be the correct answer because 80 years later, Edwin Hubble in Pasadena, over the Mount Wilson, actually from my office I can see Mount Wilson Observatory. So when a visitor comes to my office, I can actually brag saying that this is where the people discover the expansion of the universe. But anyway, so he discovered the expansion of the universe by observing how the galaxy at distance is receding from us. And this is a solution to this problem, because this means that if the universe is expanding, there must be hotter and denser in the past, namely there is a Big Bang. There was a Big Bang. So the universe began, by now we understand that the universe began in 13.8 billion years ago, and light from stars beyond that time would not have reached us. So this is exactly how Edgar Allan Poe expected the solution to, this is exactly the solution that Edgar Allan Poe expected, and this was confirmed by this type of observation. So why is the sky dark at night? This simple question had a surprising answer, that it's because there was a beginning of the universe. So in the next decade or so, we'll have lots of exciting experiments and observations that would significantly advance our understanding of the beginning of the universe, and some of which may provide a way to test string theory too. So this will be very exciting. Maybe some of the speakers will touch on that later. So the final wonder that I would like to pose is why gravity is just so. So as I said, the universe was born 13.8 billion years ago and very slowly developed to our current stage. It took a while. And that was very fortunate for us because it gave us a home, this beautiful Earth. And it gave us long time, 1.3 billion years, to evolve from microbe to Homo sapiens, intellectual enough to ask questions such as, what is gravity? So why is the universe was sort of stable and were able to accommodate us for such a long time? One reason is actually because gravity is weak. Because gravity were stronger, most stars would have collapsed into black hole, so there would be no Earth, no civilization. If the gravity were weaker, then star and planet would not have formed at all. So there would be just dust floating in the universe. So in either case, it would not have been possible for somebody to come up with a question of what is gravity. So the question is why the gravity is just weak but not too weak, so that we can have stars and planets and things like that. So one possible explanation is anthropic principle. It is just so because we exist. This is sort of a funny way to formulate the answer, but in certain cases, actually, it gives a correct answer. The famous example where anthropic principle gives the correct explanation is the distance between the sun and Earth. This is one of the very interesting questions that puzzled, again, people from ancient times. That, for example, ancient Greeks were able to measure the distance between the Earth and Moon, and rather accurately. And then with some large error, were also able to measure the distance from the Earth to the sun. And if you know how to do it, then the next thing is to try to explain it. And so there are lots of theories to try to deduce the distance between stars and sun and planet and the Earth from fundamental laws of nature. And in fact, Johannes Kepler had also the theory. So in one of his early books, he speculated that the 6 planets, so those days there are 6 planets known, have orbit of 6 spheres inscribing and circumscribing 5 platonic solids appropriately ordered. And he thought that this suggests a good geometric plan for the universe. So this is actually Kepler's model of a planet. So he tried to deduce that from fundamental principle, like beautiful mathematics. Okay. Yes. But of course, what happens is that after that, he got access to observational data by Tycho Brahe, and realized that this is not quite accurate, and then they reconsidered and then came up with the elliptic orbit model of planets. So nowadays, we know that it's not possible to derive distance from the sun to Earth based on fundamental principle. because we know that there are many stars in the universe, and by now, thanks to actually the Kepler telescope, that many of them, large fraction of them, have planets. And some are very far away from their host star. Some are very close to the host star, and those are not hospitable to life. But some of them are just so that they can accommodate life, and some of them can even accommodate advanced civilization. So our current understanding is that the distance between Sun and Earth is not determined by fundamental laws of nature, but is environmental, that it is determined just from many samples of planets, just the one which accommodate life and intellectual life. So this is exactly what the anthropic principle tells us. So the question that one may pose is that do we have to employ anthropic principle to explain other features of fundamental laws of nature? Should we give up deriving them from basic principle? Well, I don't know. This is something being discussed, and it is my hope that some of the features of fundamental laws of nature can be derived from fundamental principle, and this is one of the reasons that drive us to this type of question of what is gravity. So let me summarize the 7 wonders of gravity. The gravity is a force. Gravity is weak. Gravity is in the eyes of the beholder. And it is described by warping of space and time. And this could have been a good answer to the question of what is gravity. But it turns out that the microscopic world has quantum mechanical feature, and it has been very hard to marry quantum mechanics with gravity. And this is work in progress, and this is something that we have been discussing at this conference too. And one of the questions that we may be able to address is why the sky is dark at night, which is leading to the question of the Big Bang of the universe, and also why is gravity so weak but not too weak. So we are investigating this question, and we are meeting every year at Strings Conference, String Math Conference, to exchange ideas. And we are very happy to be able to host both String Math Conference and the Strings Conference in 2018 in Japan. So I'd like to warmly welcome all theoretical physicists and mathematicians interested in this area to this conference. So in 2018, in June, in the third week of June, we'll have a String Math Conference in Tohoku University, which is just a 90 minutes train ride from the center of Tokyo, so it's very convenient. Next week, in the following week, the last week of June, we'll have Strings Conference in tropical island of Okinawa, which is about 2-hour flight from Tokyo. We timed it so that it is actually after the rainy season and before the typhoon season in Okinawa. And I'm crossing my fingers so that the global climate change in 2 years won't displace this kind of season so much. So anyway, so thank you for listening to me, and hope to see you in Japan in 2 years.
Okay, thank you very much, Hiroshi, for the beautiful lecture. So this is a general public session. We have time for questions. We would primarily like to have questions from the general public, if possible. So don't be shy in asking your deep questions about fundamental questions. We can take them in French as well. And,
yeah, so Boris can translate.
I can translate the question
in French to me.
I may not be able to translate
French
the
questions are encouraged. Japanese question too.
Okay, let's take a question.
Actually, there are many other Chinese questions possible. People can translate. You raised your hand?
It was me, so.
No, but I guess we
we'll take this question first, and then we have over here.
Yeah,
so
okay, you can take your question.
I have a naive question. So the detection of these gravitational waves, what kind of effect does it have on mathematics of the string theory, especially enumerative geometries?
Say it again?
The detection of gravitational waves. I would like to know, does it kind of tell us that we need to do some new things in?
Well, it depends on the source of gravitational wave. So the one that LIGO is detecting, LIGO observatories are detecting, are from astrophysical black hole. So basically, the question is the wavelength. So in this case, the source is pretty big. It's a big black hole. And the gravitational field near this black hole is pretty strong, but not strong enough to be sensitive to possible modification by string theory or other quantum gravity effect. But this is still already very interesting because they were able to accurately measure the strong effect of strong gravitational field. So for example, the first detection by LIGO has already put the most strict upper bound on mass of graviton. So the mass of graviton has been measured by various sources, but this one puts the strongest upper bounds to date on the mass of graviton. Graviton in the general theory of relativity, if you naively quantize it, supposed to be massless. So if graviton has mass, it would be a strong modification. So this one gave a strongest upper bound for it. But it would be more exciting to be able to detect gravitational wave from primordial origin, that is from the beginning of the universe, because it is expected that the quantum fluctuation of space and time during the inflation era can be imprinted in the gravitational wave, some of which can be, of course, also imprinted in the B-mode polarization of cosmic microwave background radiation. And those would be very sensitive, potentially, to specific models of inflation, and then that can put constraint on inflation model. And there are lots of string theoretical constraints on the type of inflation model that you can construct. So those are potentially more interesting. So my answer to your question is that it depends on the source of gravitational wave. So the one currently being observed by LIGO probably would not. But the one that will be hopefully coming on in the next decade or so. So for example, there are lots of B-mode polarization experiments being developed. Some of that is satellite. I think I have a picture of one of them. There is a Japanese project that actually I'm involved in. So this one, it's called Lightbird. So this is a satellite observatory that's supposed to measure the B-mode polarization, sensitive enough possibly to exclude some of the inflation model. So my answer to your question is depends on the source.
Okay, thank you very much. Let's take us another question here.
Yes, sir.
Hello, forgive me in advance for this non-expert question, but you said that one possible way to make quantum and gravity theory compatible is the superstring theory. So
this is still a hypothesis.
Yeah, so that was my question. What is the state of the art? Are we done with unifying the four forces, or is there still work to do?
So to my knowledge, the string theory is the most promising candidate of unification of general relativity and quantum mechanics. And because, as I said, it contains all the ingredients to derive a standard model of elementary particle we know and has been tested. And it's consistently quantized general relativity and solves some of the fundamental questions that are posed by Hawking's information loss puzzle of black hole. And, but it has not been tested experimentally, observationally, in a sense that string theory makes lots of prediction, but we are still developing experimental observation to test that, and it takes time. So for example, as you go further into sort of frontier of science, it is taking longer and longer to verify prediction. For example, it took 50 years for the prediction of Higgs particle to be verified at CERN. It took 100 years for the gravitational wave to be detected. So those require a lot of technical advance. Even, for example, Newton's theory of universal gravitation, it took 100 years for the two objects on the Earth, the gravitational force between the two objects on the Earth, to be experimentally verified and tested by Cavendish. So it requires lots of effort, and so this the question that being asked before about, and in my answer to his question, I talked about B-mode polarization detection. So those are potentially an avenue where the prediction of string theory can be tested. And that's why currently the string theory is still a hypothesis that is still waiting for experimental verification. But since there are no other ideas in the market, so we are trying to develop this theory in particular. Thank you for asking.
Okay. Any more questions? Again, don't be shy. Okay, well, let's thank again Hiroshi for the wonderful lecture.
Thank you.
So we're going to take about 10 minutes break, and we convene at 10:25, let's say, with the next speaker, Andrea.